Good morning, everyone. Welcome to the Understanding PM Monitoring Options and Certification Requirements webinar. My name is Reagan Sokolowski, and I am a marketing specialist here at ESC Spectrum. Today, we have our Proposal Engineering Manager, Bobbi Greenwalt. She will be discussing Particulate Matter Continuous Emissions Monitoring Systems, or PM CEMS. This year, we're doing things a little differently during our webinars. As you can see on the right-hand side of the screen, there is a chat box. Type into the Q&A panel or the chat box to interact with our speaker, and feel free to discuss any topics throughout the webinar. Bobbi will answer questions at the end of the presentation. This is a small reminder that we will be recording this webinar and making it available immediately after using the same link that you used to register. We will also upload the webinar to the customer community about a week from now. With that being said, let's begin.
Good morning. My name is Bobbi Greenwalt, and I'm the Proposal Engineering Manager here at ESC Spectrum. So a quick background, I spent 14 years in the utility industry prior to coming to ESC Spectrum. I started as instrument and control and then worked my way up to project management, including the CEMS installations required for MATs. So I'll be going through some high-level information on the practical side of the MATS rule as it relates to PM CEMS. The information provided today is at an awareness level, giving you the opportunity to dive in deeper where needed for your facility. So our agenda here today, I'm going to go through are some challenges with PM CEMS, some PM CEMS options, an overview of the light scattering PM CEMS options, the PS11 requirements, a PS11 correlation overview, procedure 2 for ongoing QA, some key considerations, and some lessons learned. So to use the PM CEMS option under the MATS rule for non-mercury HAPS metals, a PM CEMS must be installed and operated in accordance with PS11 and Procedure 2. So PS11 details the installation requirements, while Procedure 2 provides the ongoing QA requirements. Continually monitoring PM presents some unique challenges not found in traditional CEMS. First, PM monitors do not measure PM directly and must be mathematically correlated to a PM value. In simple terms, this is done by simultaneously collecting PM samples via EPA Method 5 and comparing them to the output of the PM monitor. The results are then plotted and a correlation curve is developed to turn the unitless numbers generated by the PM monitor into a PM value that can be used to calculate the PM's emissions rate for reporting. The difficulty in developing the correlation curve comes from creating the PM loading levels. Unlike developing a curve for flow, where flow loads can be varied by varying the operating load, varying operating load often has minimal effects on PM. So running the unit harder may even cause the pollution control equipment to become more efficient. So achieving the PM loads required to complete the PS11 correlation will require either detuning or bypassing the equipment or re-injecting fly ash after. Since most pollution control equipment was not designed to be detuned or bypassed, accomplishing this may not be an easy task and will require some thought and planning. The same for fly ash reinjection. You'll want to make sure you think about how you're going to correlate the instrument early in the planning process. You don't want to install a monitor and then find out that you can't introduce PM sufficient for a PS11 correlation at that location. This planning may require cross-departmental cooperation and extend the timeline, so now is not too early to start the planning process. So just an early tip, decide early on if you need additional resources. An environmental consultant can assist throughout the project, including evaluation and certification if needed. So getting started, the first step in planning is evaluating your options. I grouped the options into three main categories: light scattering PM CEMS, which we'll cover here, beta attenuation PM CEMS, and metals monitoring. Each of these options will have pros and cons. While this presentation is focused on the PM CEMS, it should be noted that non-mercury HAPS metals monitoring is a potential option. Ohio Lumix has been working on sorbent traps for non-mercury HAPS metals modeled after PS12B mercury sorbent traps. Once approved, this might be a viable alternative for applications where PM CEMS and the required PS11 correlation are especially challenging. So light scattering PM CEMS look at the amount of light reflected or refracted due to the presence of particulate. This can be done in situ, so directly in the stack for dry stacks, or extractive on wet stacks where it's necessary to extract the sample to remove interference from water droplets. Beta gauges are extractive monitors that measure the attenuation of radiation from beta particles as it passes through a particulate sample collected on filter. These monitors work on batch sampling, so we don't have enough time in today's presentation to go through the plus and minuses of each technology, but it's important to note that there are distinctive pros and cons to each option. So when evaluating your options, look at the options holistically, installation and ongoing. On the installation side, don't forget about equipment purchases, installation, certification, consulting services, DAS and DCS configuration. Each option will also have ongoing costs for spare parts and consumables, maintenance labor, and ongoing QA. So a tip, start planning now by researching options. Eliminate options that are impractical or impossible for your application. Develop a list of pros and cons for potential options. Be open-minded, evaluate all your options. Each facility and customer has unique needs. The pros and cons may stack up differently customer to customer or unit to unit. Well, light scattering technology is not the only option. It is the most widely used technology. So we'll take a high-level look at light scattering PM CEMS. As I mentioned earlier, PM CEMS do not measure PM directly. In light scattering PM CEMS, the monitor shines a light source into the flue gas sample and either looks at the light scattered forward or reflected backwards. The amount of light scattered is dependent upon the particle's physical properties and the concentration, which can then be mathematically correlated to a PM concentration under PS11. So light scattering PM CEMS can either be in situ or extractive. In situ refers to direct in-stack measurement. This is by far the more straightforward method. However, the stack must be dry, above the dew point, as water droplets will also scatter light. A few of the most common PS11 compliant monitor manufacturers are TML, Durag, SICK, and PCME, which is actually now owned by CAI and VIA Group. For wet stacks, below the dew point where there is or has the potential to have water droplets, the sample is extracted, heated above the dew point, measured and exhausted back to the stack. The two options in this category are the SICK FWE 200DH and the CAI and VIA 181 wet stack. So here is a visualization of the TML LaserHawk backscatter and the Durag 320 backscatter and the 808 forward scatter. These are all single port installations. They also have similar footprints and look and feel to the other offerings in each of the manufacturer's lineup. So if you already have equipment from either manufacturer, learning the PM CEMS shouldn't be a far stretch. And here is a visualization of the PCME 181 wet stack and the SICK FWE 200. You'll notice that the layouts and footprints of the monitors are very similar. In both cases, the sample is extracted via nozzle at the end of the probe, heated above the dew point to remove the water droplets, and brought across the light scattering measurement device, then exhausted back to the stack. It's important to note that the probes used in both applications are the respective dry stack monitors, so the Stack 181 and the Dust Hunter SP 100. A key installation note, which holds for both monitors, is you'll need to install the probe below the monitor at an incline, 6 degrees for the PCME and 15 degrees for SICK, to allow for drainage back to the stack. So installing the ports low will allow you to access the monitor without a stool or a platform. Both monitors are offered with multiple nozzle sizes. The nozzle size will control the velocity of the flow through the monitor and is selected based on the stack velocity. One difference to note between the two monitors is the PCME has an option to vary the sample rate to maintain isokinetic sampling. SICK does not. However, they do provide a statement in their manual stating that the measuring behavior of the FWE 200DH is mainly independent of gas velocity changes in the duct, therefore isokinetic extraction is not required. So out in industry right now, the existing PM CEMS, here's a breakdown of the installed monitors for both wet and dry stacks. This is provided by RTP Environmental Associates, according to the last check that they've done. So SICK does hold the largest market share on the dry stacks, followed by TML, Envia, PCME, and Durag. SICK also holds the highest market share on wet stacks with their FWE 200 and the newer FWE 200DH, followed by PCME and the MSI BetaGuard. The MSI BetaGuard is not a light scatter device, that is a beta attenuation monitor. So once the monitor is installed, the initial certification is completed under Performance Specification 11. Prior to certification, a conditioning period is recommended. During the conditioning period, the PM CEMS is operated over a period of time to assess the PM response over a full range of operating conditions. Prior to completing the correlation, the monitor needs to pass a 7-day drift test. As I mentioned earlier, the monitor produces a unitless number and must be mathematically correlated to a PM value. And that is done through the PS11 correlation. So how is it done? Keep in mind, this is a high-level overview. You'll want to dig into it deeper before you go to do it. But the basics of it is that you will need 15 method 5 test runs over 3 particulate loads. So low at 0 to 50, mid at 25 to 50, and high at 50 to 100. The output of the PM CEMS during each run is plotted against the reference method results, and a correlation curve is fed to the data. There are 5 options, so linear, log, polynomial, exponential, and power. Most curves are programmed into the DAS. The raw data from the PM CEMS is brought into the DAS, and then a correlation curve is applied. Once you have a PM concentration value, it will need to be converted to standard conditions, which will require temperature and pressure readings. So an important note when doing this is a lack of range can result in curves that are not representative of the overall monitor response. So while PS11 does give you some flexibility in the levels, 0 to 50, the 25 to 50, and the 50 to 100, getting a good range over your full operating limit will give you a better curve and more repeatable. So why is it difficult? The difficulty comes from creating the 3 PM levels. First, pollution control equipment is not designed to allow PM to pass through, and PM doesn't change sufficiently with operating load. Therefore, you will need to develop a detuning or bypass procedure or re-inject fly ash. PM runs can be long in order to collect enough sample. You'll need to hold the process conditions steady throughout the run. You'll need to ensure that the process is stable before beginning the run. The new rule also stipulates a minimum collection per run. The time it takes to switch from one process condition to the next and stabilize before beginning the next run will vary. and it may take minutes to hours depending on your methodology, so you'll need to build this into your testing schedule. So detuning or bypassing versus fly ash reinjection. When developing a detuning procedure, there are a few important considerations. First, consistency is crucial. The process conditions need to be stable and repeatable, both from run to run and also when the RCA is due under procedure 2, typically in 3 years. Also, is your methodology representative of the actual process upset that the monitor will need to read? Your procedure may require pre-testing prior to the correlation. And in the end, detuning may not be an option for you. So fly ash injection may be a viable alternative. In fly ash reinjection, your own fly ash typically is re-injected into the process after your last piece of pollution control equipment. B3 Systems has developed a methodology to re-inject the unit's own fly ash to achieve those PM loading levels required. It does require pre-planning. You'll need to collect, store, and deliver fly ash. I can tell you that 55-gallon drums work, and you also need to have a viable upstream injection point. And don't forget to determine your required plant resources and plan accordingly for things such as an appropriate staging area, power, and an air supply in order to do the injection. So it doesn't end at certification. So once you've installed a PM CEMS under PS11, you'll need to maintain the monitor according to procedure 2. So here are the highlights. You'll want to familiarize yourself with the requirements as they pertain to your PM CEMS. Once again, these are the highlights. You want to review procedure 2 in its entirety. But you will need daily zero and upscale GIF checks. These should be automated, similar to the daily checks that are done on flow and opacity monitors. Daily sample volume checks for monitors that use the sample volume to calculate your PM concentration. These will be required on beta attenuation monitors that do batch sampling. Since light scatter monitors do not use the volume to calculate the PM concentrations, these will not be required on the light scatter monitors that I covered earlier in the presentation. Next, you'll have your quarterly ACA, which is your absolute correlation audits. It's a 3-range check similar to opacity filter audits. The monitor is challenged at 3 levels, and the technique will be determined by your monitoring type. For light scattering PM CEMS, this is typically done by inserting optical filters. Once again, very similar to the way that you would do a opacity filter audit. Next are the quarterly SVA, which is a sample volume audit. This is the quarterly check on the sample volume when sample is used to calculate PM concentration. Once again, these will be required for beta attenuation monitors and not the light scatter monitors. Next, you have an annual RRA, which is a relative response audit. It's a 3-run stack test done at found operating conditions to verify the correlation curve. And then there's the 3-year RCA, which is your relative correlation audit. This is a more intensive 12-run test to verify the correlation curve. This is where you will need to be able to repeat the PM load levels similar to the initial correlation. Your initial correlation PM loads being reliable and repeatable will pay dividends here. In addition to your procedure 2 requirements, you'll need to consider spare parts, developing a QAP, though I do recommend completing initial QAP prior to certification and updating as needed, training, prints, ongoing maintenance and repairs, and it's never too early to plan that replacement schedule. 10 years is generally a safe planning lifespan. So a tip here, documentation. So retain your planning and PS11 correlation notes. You'll need them when RCA and or replacement or recertification comes around. So equipment specifications, including your model and serial numbers and prints, will make repairs and replacements easier. Plus, you'll need them for your hard copy monitoring plan under Part 63. And a bonus tip, be ready for a surprise RCA. If the RRA does not meet the Procedure 2 requirements, the more intensive RCA will need to be completed. When planning the annual RRA, be ready to recreate the PM loading levels used during your initial correlation if necessary. This will require elevating your PM levels as you did during the initial correlation, though through detuning or fly ash reinjection, which can be difficult on short notice. So have a backup RCA plan ready. You may even want to check the availability of the necessary resources in case they're needed on that short notice. So some key considerations, selecting your monitoring location. Yes, it must be representative of your flue gas stream, but can you detune or inject upstream effectively? Timelines. Install early and note how the monitor reacts to a full range of operating conditions. Expertise. Do you have the necessary expertise in-house, or do you need to hire a consultant? Detuning and injection will involve plant operations and engineering. Involve them early on in the process. Talk to your stack testers. Are they experienced in PS11? Can they help you develop the curve? Consider on-site analysis. This will allow you to review your correlation progress real time and make adjustments as needed. Highly recommend that you do this if possible. So how are you going to program the curve into the DAS? Because it is typically done in the DAS rather than the instrument. Can you do this in-house, or do you need outside resources? Keep in mind that this will be a two-part configuration when you do this. First, you have to bring the raw data into the DAS at the initial installation. And then you'll have a second configuration to apply the correlation curve and correct to standard conditions once your correlation curve is completed. So interacting with the reporting agency. So each state can be different, and you may need to discuss pre-testing correlations. Recommendation here is if you have peers within the same reporting state, you may want to talk to them and find out what their experiences were, because it may be different. So some lessons, apologize there. So some lessons learned. Planning. Involve all key departments. Don't forget to include environmental, operations, engineering, IT or OT for your DAS and your plant control systems. They all have a stake in the game, and involving all groups from the beginning will help your installation become a collaborative effort. Installation. Install the monitor early. Observe its readings. You should be able to determine which operational parameters affect PM. This conditioning time prior to completing the PS11 correlation will also provide time to learn the operation, maintenance, and QA for the monitor. So a side note, although much of the spotlight is on the correlation curve, keep in mind that you also have to do a 7-day calibration drift test, and you'll need to put this into your timeline. When you go to complete the PS11 correlation, consistency and repeatability is key. This best strategy is simple, effective, and repeatable. Keep notes on the unit operating conditions while performing the PS11 correlation test, as well as how the PM levels were achieved. So resource considerations. Not only do you need more resources, those resources will require more coordination, so be prepared. One resource you'll need to make sure you line up as I said earlier, was stack testing with on-site analysis. Having this on-site analysis will allow you to know how well your correlation is proceeding and to make adjustments on the fly as needed. So talk to your industry colleagues. Many lessons have been learned since MAPS first came on the scene. Learn from your peers' successes and failures, and knowing your plan B and C, D, and E before you need it will save you a lot of time, stress, and money. So that is the end of my presentation. If there are any questions, I can take them now.
I do see one here. It is from George Marshall. He said, is RCA every third year or 3 years RRA, then an RCA the fourth year?
I am going to double check that for you. I believe it is every 3 years and an RCA, not that year, but let me double check. Reagan, do we have a way to get the answers for follow-up answers?
They can email you, or I can, George, if you want to send your email, actually, you can send it in the question pane. I can record that, and then Bobbi can follow up with you if that works.
Yeah, and George, I'm pretty sure that that's the answer, but I always run everything through our regulatory specialist just in case.
Okay, we've got George's email now. I'll copy that.
Perfect.
And then we do have another question from Deb Nelson. Do you have any preference for front scatter versus back scatter?
So the manufacturers will tell you that the forward scatter is going to be more accurate. However, that's overshadowed by how well you do the installation and how well your correlation is done. So forward scatter versus back scatter isn't as important as getting your correlation done and done right. What I would recommend is that you look at your process conditions and select a monitor that matches your process conditions. So it may be that a backscatter works better for you, and if you get the correlation done, that difference in accuracy probably isn't going to hit. All of them have been proven for PS11 compliance, so you would be good to go.
Perfect. And then we've got another one from Trey Lightsey. Will the PS11 curve be programmed directly in an 8864 module or possibly handled with math channels?
So this is a Brian Perloff question. He's one of our principal engineers. He's been working on this, but typically, I did ask him about this ahead of time, and they usually use math channels, because what they would do is bring in the raw data so that you can see the raw data, you can see what your PM response is, and then apply the correlation curve to it through a math channel, and then apply any your correction to standard conditions. And so he does have some basically best practices and recommendations that I would highly recommend reaching out to him if you have any questions for that.
Beautiful. Here is another question from John Shimshock. Do you have any suggestions for operating a PM CEMS in a wet FGD stack to avoid probe plugging issues?
Yeah, so that actually is where I'll actually go back a couple slides here. So you'll notice that in these modules that for each of the probes, the PCME, they recommend like a 6 degree, SICK recommends a 15. And the reason for that is to allow drainage back into the stack without plugging. And that's also why you typically install that port low, and so your monitor can be well above it, and you're keeping everything sloped back down to that port so it can drain. And then I assume that you're also talking about, the inlet where you would have your nozzle, and that is just regular maintenance and cleaning. So if when you install these, you install them somewhere that you can get to them for regular maintenance, because when you have a process that's wet, you may have some particulate, some buildup on that probe. You will want to be able to clean it out.
And then we also have John Rampola. I think he has the answer for George. An RCA conducted during the period is conducted during the period, and an RRA is required and can take the place of the RRA for that period.
Thank you, John. That is what I believed it to be as well. So I do appreciate the confirmation.
I'm not seeing any other questions, but if you do have additional questions, you're more than welcome to email myself, rsokolowski@escspectrum.com, or you can shoot an email to the marketing inbox, which is just marketing@ESC Spectrum, and I can relay that to Bobbi. Or if you have Bobbi's email, you can email her directly. But I think we're good to go. So thank you so much, Bobbi. You knocked this one out of the park, and I appreciate everyone for participating. I hope you guys have a great rest of your morning and your afternoon, and enjoy the rest of your week. Thanks, everyone.
Thank you, Reagan.